Let f of x equal x cubed plus 6x squared minus 4, and calculate the derivative f prime of x. Okay, since this is a polynomial, it's very simple to use the power rule here. So 3x squared plus, oh, not 18, that would be 3 times 6, 12x, and the value 4 is a constant, so it would have a derivative of 0. The second derivative would be 6x plus 12. On what intervals is f increasing, and then on what intervals is f decreasing? Well, the function is increasing whenever its first derivative is greater than 0, and it's decreasing whenever its first derivative is less than 0. In order to determine this, we need to do some testing. So if I take the zeros of my first derivative and place them on a number line, and I'm just going to use the zeros because there are no places here in a polynomial function where we need to worry about a location where the first derivative is undefined, because these polynomials are smooth continuous curves, so easy to work with. So I will set the derivative equal to 0 and solve that. So first off, I notice there's a common factor of 3. So I could take that out. Actually, since there's only 2 terms, I could do better than that. I can take out a common factor of 3x, which would leave me just x plus 4. So that gives me a 0 of 0 itself and negative 4. So here's negative 4, and here is 0. Now, in order to determine where the function is increasing or decreasing, I need to check on each of these intervals what's happening. So I have to pick some value within each interval, and I just choose the smallest numbers that I can possibly get, and then plug it into the first derivative to see if it's positive or negative. And I generally use this factored form because it's pretty easy to plug a number in there. So 3 times negative 5 would be negative 15, and negative 5 plus 4 would be negative 1. So negative times negative gives me a positive. Then at negative 1, 3 times negative 1 would be negative 3. Negative 1 plus 4 would be positive 3. So negative times positive is a negative. And 3 times 1 is 3. 1 plus 4 is 5. So that is positive there. So now I can interpret here. I am increasing on the interval from negative infinity to negative 4 because the derivative is positive there. And I'm increasing from 0 to positive infinity. On what intervals is f decreasing? That's already answered here in my chart, just wherever the first derivative is negative. So from negative 4 to 0. On what intervals is f concave downward? Well, concavity is determined by the second derivative. So the second derivative, whenever it is less than 0, you're concave down. And whenever it's greater than 0, you're concave up. So what we're doing here is essentially the same process that we did with the first derivative. We're just doing it with the second. So we start off finding the zeros of the second derivative. So I take 6x plus 12, set it to 0. Then that gives me effectively 6 times x plus 2. So I have a 0 at negative 2. All right, so negative 2 is called an inflection point, or it's a potential inflection point, I should say. And I pick values inside the intervals surrounding this number. So the smallest, easiest ones I can. And I plug those into the second derivative and see if I get a positive or negative answer. So if I plug in negative 3, that would be 6 times negative 3 plus 2 is negative 1. So that's a negative value. If I plug in 0, it would be 6 times 2, and that's a positive value. So what that means is whenever I'm concave downward, the second derivative is negative. So on the interval from negative infinity to negative 2, and that leaves me to be concave up on the interval from negative 2 to positive infinity.